Hello and welcome to this new lecture, which is a continuation of the current discussion we have on rule-based systems. Yeah, I hope you enjoy it, and yeah, let's go to work. So that's lecture 9, and we discuss today some examples of rule-based stochastic processes, and also will now for the first time introduce the Gillespie algorithm and some variants. Okay, so we just right away dive into the problem, and we first introduce a kind of more conventional problem from, let's say, reaction systems. So that is a simple cell cycle model. It is also an interesting model because, for our purposes, because it's not it's not a chemical reaction system. It's really a cell biology problem that was originally translated mainly by Tyson and co-workers into the setting of reaction systems. So it's good to have this example because it's a very early example of modeling with what we call now rule-based systems. Well, what do we have here? So you know perhaps that the cell cycle is a very fundamental process of every organism that is on Earth today. So all organisms are cell-based, and in order to be able to reproduce, the cells need to divide. They need to divide in unicellular organisms, of course, but they also have to divide in multicellular organisms. And in multicellular organisms, of course, cell division is also related to, well, things like developmental biology, but then, of course, also repair of tissues, etc. So this is a very important system to understand. And after a lot of research, people have found out, so biologists have found out that there is a certain protein family that is responsible for, let's say, triggering the cell cycle, and that is here the cyclin family. And you have to, for the purposes here, you have to think of one of the cyclins being a kind of clock inside the cell. So if the concentration of this cyclin is high enough, then this is a signal for the cell to divide. So more or less that is the kind of story we need to understand here. So the cell cycle has different phases. Here, for example, there is mentioning of the G2 phase and the M phase, which is mitosis. So let's see what kind of basic rules we have for this model. Maybe we first have to go through the types as usual. So we, also here we will have types to consider. So first of all, we have here something called M and M+. These are the active and inactive concentrations of so-called MPF, which is the mitosis promoting factor. So what we have here in this model in general is that we have an assumption that the proteins can be in two configurations, and that can be the active configuration and an inactive configuration. And throughout the notation we use plus for the active form, excuse me, and no superscript for the inactive form. So besides this mitosis promoting factors, we also have proteins called C and W, and these proteins that are described by the type C, they are exactly one of these cyclins, so that is CTC25. And yeah, and also W will be one protein that is from the MIT1 family of protein kinases. Okay, so let's have a look after looking at or after an explanation what the players, the types are in this model. Let's have a look at some of the reactions or rules in our new terminology. We have that this cyclin in the inactive form is coming together with the mitosis promoting factor, and then the mitosis promoting factor here is assumed to be deactivated. Yeah, so that is what you really could say here, is that this is a rule where the cyclin is somehow acting as a just as a catalysator. So here you see on the left hand side and on the right hand side that it's unchanged after the reaction, but there is just a deactivation here from M plus to M after the event happened. Now let's look at the next one. Here we have an inverse kind of thing. So here we have M and M plus. So you see that the mitosis promoting factor in this reaction gets activated, and the catalysator is here the W, the V1 protein. Now in the next reaction we have the fact that there also can be deactivation. So here comes in C plus on the left hand side. So the cyclin is active and then gets deactivated by the mitosis promoting factor. Then there is also the possibility that we have a spontaneous activation of the cyclin with a certain rate, which is K4. I forgot to mention the rates here before, but they are in the conventional way written above the reaction arrows or rule arrows. Yeah, and also there is spontaneous deactivation here of the V1 protein with rate K5. And then finally you have also one possibility that the V protein is activated through the MPF, the mitosis promoting factor. So I think this explains the model well. You can see that this is a kind of cyclic arrangement where you have a constant build-up of active and inactive forms of these three proteins that are considered to be very important in the process. So that's a nice old model which you should be able to interpret correctly. So yeah, have an intensive look and get used to the notation with these arrows describing events. Yeah, I would already give you a look at what will be the type graph of this model. Remember, we introduced type graphs already before when we looked at structural models and introduced classifications. So here we have the same, but I will give you, in this context of rule-based models, I will give you a more precise definition of this rule-based model, which will be based on the complexes to the left and to the right of the rule arrow. So just have a look. You can see a lot of interaction here going on in the middle. Also indicated is that here we look at a state space, which is just counting the molecules in a cell. So that is that we have a state space here at each of the proteins, which is given by N0. So you can have no molecules, or you can have arbitrarily many of them, but they are countably many. Now we go to a completely different field. We go to economy. The motivation is twofold. On one hand, of course, I would like to argue that these rule-based models can be applied everywhere. So economy is a very good example for that. But on the other hand, I also need an example for what we call rules of amount. So we want to see how something that is not countable, like energy, or also something like economic size, how this actually can be modeled with a rule-based approach. So let's first discuss a little bit the different types we have to minimally introduce for a very rough economic model. So what we have here is first of all some capital. So capital in a certain sense plays the same role as energy, I would say. I mean, it's not a precise similarity, but the capital drives in a certain sense the economy by, paying for labor, paying for innovation, new machines, etc. And also, of course, you can save money. We will come to that in a moment. So the capital is very important. And then the model will also depend on E, which is a type which is describing the size of the economy. So the size of the economy will be assumed to be something that we cannot count, but it will be treated like a substance. And so these are the two state spaces. So you have capital and you have economic size, and the two things interact with each other through different ways. So let's first start with the economy itself. I guess that's also how it started historically before capital was invented. So the economic size is something, the more interactions you have inside the economy, the bigger is the economic size. Nowadays there is a tendency to measure economic size, for example, in GDP. Whether this is exactly what we are modeling here, I will have to leave open. But in any case, you have to invest into the economy. So there will be an arrow going from the capital to the economy. And this will be done by a certain rate, omega. And unfortunately, as we all know all too well, the economy is never something that can stand still. So there is always some depreciation. That means if you have machinery, the machines become old-fashioned, or they just don't work anymore. So there is a certain loss rate in the economy, which we model by mu. But you can also, of course, get wealth out of the economy. That is also very important. So if you made good investments and the economy works well, then you should also be able to generate capital. And this is done via the saving rate sigma, which is drawn here. Then of course it is important to understand that in the end the economy should of course serve human population at the moment, at least before the machines have taken over. So there will be a certain rate gamma, the consumption rate, which of course will use capital. And yeah, that is something we model to be, depending on, or it will be a drainage, so to speak, from the accumulated capital, and not directly a drainage from the economy. So the idea is, of course, that we buy certain products and then consume them. Yeah, but also, even if you don't consume, you also will have a certain loss of capital, and that is what is usually called inflation. So you have an inflation rate, which we model by alpha. That's more or less all the flows in this two-type small economy. And now we have to get the idea formulated as rules. So here are the rules. First of all, so this rate gamma, which you remember was here the consumption rate, means that we have a loss. Remember that we use here this empty set symbol to notify that something is going out of the system. So both gammas and alpha was the inflation rate, which you can see here. They are just losses of the capital. So these two events are pretty clear. Then you also have that the size of the economy is shrinking by this depreciation rate mu. So this is also a loss out of the system. But now we have to go through to the middle here, which is the more interesting thing, because this is the kind of interaction between the capital and the economic size. So how does that work? We have that the economy, a fraction of the economy is with a certain rate sigma, and the fraction is given by rho, is becoming again capital C. So that is the arrow that goes from here to here. And the other rule is more interesting, even more interesting. So a certain fraction of the capital, so that tau, somehow you can think of it, is it a little bit like innovation? So this is a kind of efficiency, how to use capital. And the nu is a kind of efficiency, how much of the economy you need to produce more of the economy. So, and there is also a certain rate omega involved. So these two things, so a certain amount of capital, a certain amount of already existing economy, is creating more economy with a rate omega. Okay, so this is the model, and we will see in a future lecture how this model actually behaves. Will be very interesting. We will very much later also look at a dynamical system that is based on these rates and rules. Right, so here is just a little bit more explanation of the types, which you can have a look at in the slides coming with the lecture. And also it should be seen that there is also an interaction or type graph involved, and here at the moment the most important thing is just looking at the state spaces. So both state spaces of capital and the economy are now something that is not supposed to be counted, so it's not n0 the state space, but it's the positive real, or better the non-negative real numbers which are creating or which are used for creating the state space. Yeah, now we come to a third model, and that is a behavioral epidemiological model. I thought it would be interesting to have a little bit a more complex model in the lecture, and I also thought, of course, because of the current pandemic, that it would be very nice to show you that the rule-based model are exactly the type of models that can be very successfully used to describe the pandemic situation. So here we have, I hope you find that interesting, a deviation of the SIR model. So we have first, you can think of this model as starting as an SIR model. So you have just 3 types at the beginning, and they are just susceptibles, infectants, and recovered individuals. So the basic objects here are human individuals, of course. But now we introduce something we can call locations, and they will also be associated with certain type of behaviors. So locations can be anything like, say, let's say, for example, they can be pubs. They can be universities. They can be, of course, home. They could be, very importantly, also hospitals. They could be supermarkets. All the kind of things you have to visit when you are a human individual. Could also be schools, etc. And because usually such a list which refers, of course, to where people are, maybe mainly, or at least a large part of their time, and how likely it is, of course, that you get infected. That is, of course, a statistical problem. You need to read that out of the data. But we are very flexible with our model here, so we can reflect all these statistics that possibly can be done. And so we introduce a subindex beta here, which is a subindex to each of these types SIR. So we have a lot of subtypes, and there are beta bar many of them. So what you have to think of, for example, look at the susceptible individuals. So the susceptible individuals have a subindex beta, and this is whether they are in pubs, whether they are at universities, at homes, supermarkets, etc. So this, of course, also has a certain behavioral aspect, because, for example, if you go to the pub, that is a kind of behavior. If you go to hospital and if you are sick and you have to go to hospital, that is not so much a behavior, it's more a necessity. But for example, some employers might allow you to work from home, so the workplace might be a certain type of behavior, or a certain type of behavior might be involved. And how much you stay at home, for example, is also a little bit your choice. Okay, so we assemble all these index in an index set which we call phi, and now I have to explain you the rules which govern the game. So first of all, we assume that inside each of these locations there can be infections. So this is the usual SI mechanism, so a susceptible individual and an infectant come together and they create two infectants. So the infectant again is in the biochemical sense a catalysator, converting the susceptible into an infected individual without changing its own type. So this is all happening now inside locations. That's a nice way to model, for example, certain dangerous places, because then you can have, for example, in pubs, say, which are not, where people are not very much into social distancing or something, you can assume there is a very high infection rate, I beta here, for such locations. Whereas at home, if you are staying at home, then the I beta here is very, very low. Of course, there is also cross-location infection. So somebody who was in the pub the evening before now can also be in another place, and this will be modeled by these cross-location infections. So this is this line. And then you have the usual recovery of an infected person. That fortunately also happens in the current pandemic. And now you have an assumption that you can switch locations with certain rates. And some of them, of course, are again behavioral. Others are just imposed on the person, but it doesn't matter. We don't differentiate here between these two patterns. In any case, you can switch locations from any place to any place. So that is written here. So beta prime can be in this index set. And switching places, of course, is independent of your state in the epidemiological context. So S, I, and R, they can all switch places. This is, of course, a little bit a kind of statistical thing. So you should not think of this as a model where people, switch places all the time. And we would model that. That would not be a good idea. This is more like behavioral changes. So, for example, somebody who was in a pub all the time now sees the pandemic is getting worse. So there are more infectants around him. And then, for example, he never goes to the pub again as long as the numbers are high. And that would be a typical thing we can describe by such behavioral switches, which means you are switching locations. So you switch, for example, to stay home instead of going to the pub, or you go less, or you only go, to supermarkets that are safe, or you think are safe, or something like that. Okay, so that is the epidemiological model. And yeah, so for our purpose, it's a good idea to have a linear order on these models, on these locations, sorry. So you think that with you start with the lowest index. That would be something like being at home and relatively safe from the disease. And when you reach higher and higher indices of locations, because locations are ordered by their, let's say, by the danger to get infected. So the most dangerous category then, or location, would be when the location index is equal to beta bar. Okay, so that's this model. The next thing is I want to discuss some structural models that can be associated to each of these models. That is giving now a link to the previous lectures on structural modeling. And the first thing I want to introduce is the complex hypergraph. Now we know what a hypergraph is. How can we associate that with a rule-based system? Well, here we do it via the complexes. So we look at the complexes as being the set of vertices. And yeah, we are drawing an edge from the complexes to the types. If for a certain rule the left-hand side or the right-hand side complexes are containing these types. So it's a kind of indeed a way to to illustrate who is taking part in events. So which types are taking part in events and building up which complexes. So maybe I illustrate that with a cell cycle model. So here on the left hand side I have drawn the cell cycle model complexes as a hypergraph, and here I have the same illustration as a bipartite graph. By now we know, of course, that the two structural models are completely equivalent, and this you should check in this example. So an interesting take-home message is that the complexes of all the rules which define a rule-based model form a hypergraph, and that is the form that you find for the cell cycle model, for example. And this is the form you find for the economy. So the economy here has actually three types. I said previously only two, but here, because we have a lot of flows inside and outside the system, you should incorporate here outside the system as an additional type. Another directed graph now, instead of a hypergraph, is the so-called reaction graph. That is a straightforward construction. You just think of the arrows from the rules as being arrows in a graph. So again, the vertex set of this graph are the complexes. And if there is a certain rule which takes two complexes C1 and C2, and there is a rule between them, then you say these are two vertices that are having an arrow between them. So it's very straightforward to look at the rule graph. So here for the cell cycle model, you have these 6 reactions or rules, and you right away can write down here this rule graph for this model, and it's the same for the economic model. Again, you can just write down the rule graph like that. It is interesting to understand that the combination of the complex hypergraph like this one and the rule graphs like this one are actually having all the information of the rules that is needed for its description. As a formal description, as a set of rules. But if you want to know a little bit about, let's say, what are the ideas about how the different system components here, the types, interact with each other, and that was, as you remember from previous lectures, also the fundamental idea of the type graph, then you should look now at the interaction graph. So each of the rules first defines a certain single interaction graph, and later we will look at the union of all of them, going through all the rules, and that will define a total interaction graph of the system. Okay, so let's first pick out a certain rule, Rj. Yeah, then we have a weighted graph where the vertex sets are the types in this way. So the types, the vertices of the source side. Remember, this superscript is for source. Are all the types that are in this source complex, and then you also have um, the target side. So here is actually an arrow which I just spot. So this should be not an S, should be a T. So this vertex set VJT is the vertex set of all types which are in the target complex of this rule or reaction. And now we also weight possibly arrows, and this is with a plus and a minus sign. And the idea is that the plus and the minus sign is telling you something about whether this is a positive feedback or a negative feedback. So how one type is positively affecting another type by, for example, increasing its numbers or its substrate, or whether it has a negative effect. But now, of course, you must be able to construct the errors. So there are three procedures to do that. The first one is here. Now we look first at some type at the source side of a rule, and we look at some type then on the target side of the rule. And if the VKJ here, VKJ is positive, which oh no, sorry, if the new KJ is positive, then we draw an arrow here, and we have also a positive weight on this arrow. Now if the new KJ is negative, then again we have an arrow from Ti to Tk. So you have to remember that these are of course ordered relationships, and then we have a negative weight on this arrow. And if we have a type in the substrate set, in the source complex Ti, and if we have a type Tk on the source side, then we also draw an arrow, and we have here a negative effect. The idea is that you have here consumption. So if two types are together in a source complex, then this means they get transformed, or one transforms the other if one is, for example, a catalysator. So they will have an interaction with each other. This is modeled here in 3. Whereas this is a typical model, in 2, this is a typical case where you have that some substrate is actually converted into something else, and therefore it's consumed, and that explains that you have here this negative impact. And if something is consumed but created on the other side, but it has a positive net production that is described by this new Kj. So this is of course the entry of the stoichiometric matrix. So if there is net production, then this feedback is weighted positive. Okay, so this needs a little bit of thinking, but definitely, we didn't have this notation before, so this is the k-jth entry of the stoichiometric matrix. And also here. So the net production can be positive or negative. We discussed that in the previous lecture. Okay, let's continue. Now, as I said before, this was now something that was defined for each reaction or rule, and now we combine all these individual arrows into a large interaction graph, and this we do just by looking at the total vertex set, which will be the union of all these Vj vertex sets, and then we also combine all the arrows by looking at the unions of all these arrows. And now actually we can go back to some of the previous figures, because I have already shown you some of these interaction graphs. So for example, for the simple market model, we have here the following situation. So I didn't draw here the weights, actually, the plus and minus signs, but I did draw the arrows. So that definitely means that there is some effect, which we also, of course, would have guessed, so even without a formal definition, that the capital must influence the size of the economy, and the size of the economy by the saving rate, remember, will also influence the size of the capital, of the accumulated capital. And we have, of course, some negative feedback here, which is by the depreciation process. So the economy will not stand still. If there is, for example, no capital flow, it will actually shrink. So this is most likely a negative feedback. There will also be some more cycle here. Also, the capital cannot just be on its own. It has also a negative weight, because there is inflation, remember, and also consumption. So this will create a negative effect on each other. And well, in any case, let's see, we just have to follow the formal definition. I'm not sure this graph is entirely correct, but in any case, because I was just thinking, of course, what we have here is we have included in this graph the outside of the system component, which we defined by the empty set notation. So that means, for example, that something like inflation that is actually modeled by the arrow here, so I should not include it as a feedback on the capital itself. And also the depreciation is the same here. So we have to check if actually this feedback loop is there or not. So we will discuss that in the lecture, perhaps. But you know what I'm trying to do here. So I want to draw the interaction graph for the simple economic model based on our definitions. So if you follow the definitions closely and you compute the stoichiometric matrix, which you can also, of course, compute for the substrate or substance-based approach. Then you should be able to also to compute here the weights on the interaction graph. Okay, so let's go forward. So we discussed the interaction graph, which is a very important model ingredient, because it is so, I should emphasize maybe that the interaction graph is a kind of bridge between structural modeling and dynamic modeling, because it shows you possible behaviors of the system. For example, if you have only positive feedback loops which are not balanced by some negative ones, then you can guess already at this stage that somehow the system will explode, because everything will just get more and more and more and more. And yeah, so that of course can happen, but yeah, so there are certain conclusions you can make from the structural description by the interaction graph on the dynamic situation. That is exactly the thing I like to discuss today. Okay, now we have to go to the master equation. So we need to be able finally to describe the rule-based system based on some equation which controls the system state at a certain time t. So we introduce a probability, which here is given by p, and that is, that is defined as the joint probability that for counting rules, of course, where we can count objects, that the system state is in some configuration small n, which is a vector of as many of these non-negative integers for each type. So we have n1 is how many particles or objects there are of type 1, and ns is how many objects there are of type S. So this configuration is now shifted in time by this joint probability that is depending on time, and for which we in a second write down an equation. Yeah, so we will have for the system, of course, one of the two stochastic updates, so either the Gillespie update or a generalized Gillespie collision update, and therefore our events are discrete. So you can always imagine here in this context objects have to bump into each other by some process and trigger the discrete event in time. And so the total equation you will have is something like that. Let's go through this. So this is the joint probability that at time t you see the configuration n. Now we will have to introduce this transition probability p of mn. So this will be the probability that you jump with one event from a configuration n into a configuration n. And the m here, that will be the so-called successor state. Let's go to this page for a moment. So to look through the notation. So here we have these two states, S of n and T of n. So S of n is defined to be the set of all configuration that can terminate at some configuration n, after one rule event. So one event was triggered. And T of n is the set of all stands reachable from n in one step of the feasible rules. And why do we call them S and T? Well, you see that here. So the notation is meant to suggest the source and target states at n. So one could also call S of n the predecessors of configuration n and T of n the successors of state n. So keeping that in mind, and also keeping in mind that P of nm delta Ti is the probability per unit of time that after time delta Ti there is a transition from configuration n to configuration m, we can now finally go back to the master equation and understand it better. So we have here, the change of the probability that at time t we can find configuration n, and t0 and n0 had been the initial conditions when we started to look at the system. So now we look at all successor states S of n. So we look at states that can terminate at n. This is here. And this is of course like that. So we have this joint probability that we are at Tm at time t, and at time t exactly we have then one of these transitions from n to n, and therefore we exactly arrive at a configuration n. So this is one possible path. Another path, of course, is that we actually go away from n. So in order to arrive at n, we could have been already at n, but then go away from the configuration n, and this will be done by this inverse transition from n to m, and it's also weighted by the probability that at time t we had been at configuration n. So here you see we had been at configuration m, and we jumped to configuration n, and here we had already at configuration n, and then we jumped away to a configuration m. So this explains you the master equation. It's interesting to see that so this is based on events, so we do actually have here continuous time t during which certain events can happen, and we have these discrete transitions here on the right hand side. So this is an interesting kind of mathematical equation. So it's discrete and continuous at the same time, and that is because the discreteness here in time comes by the event structure. Okay, I think we have understood that. Now we transform the master equation a little bit by using the rules or reactions. This is done with the help of the stoichiometric matrix, because the stoichiometric matrix actually tells us how many particles are either created or destroyed by certain events. So we can now look at equations like that. We know that certain configurations, let's say m, is reached by a configuration n minus the stoichiometric entries from the chase reaction or events, and that we previously denoted by nj. So in the same way, of course, you can also say that m is n plus j, so you can compute actually the predecessor and successor states of n with the help of the reactions and the stoichiometric matrix. If you do this, then you get a reformulation of the master equation, and that is in terms now of so-called propensities. So we introduce for the first time a propensity. So each reaction now has associated to it exactly one propensity, which we call Rj. And here the argument of the propensity will be a certain state. And this is exactly the state n minus nj. So you have that you have been at state n, and now the jth rule is applied. So you get this new update, and this is for the case where you have been previously in a state n minus j, and then if you apply this propensity, then you exactly end up in n, and you have to subtract again all these propensities where you had already been in the state n with a rule j, and then you went away from it. So the summation now is over all the rules, and if you remember, we always assumed that we have exactly r many rules, so the sum here goes from j equals 1 to r. Okay, so the big difference here is now that we have a reformulation of the master equation in terms of reactions or rules. Now I should say a little bit how this works with rules of amounts, and the short answer is it works exactly in the same way, just we are not counting here anything, we just have a fixed stoichiometry, but the state space of course here is real valued. So we know by the stoichiometry how much of a substance or energy or whatever is lost or gained, and this is exactly how we formulate again these propensities. There's no problem in the formulation on that level. We have now to define, of course, the propensities which occur in the master equation. And remember now that previously we had two possibilities. One possibility was that we had a constant weighted rules. So this was related also to chemical reaction, if you remember, where we just have a constant reaction rate. So we define in this case the propensity, which is depending on a certain configuration n for the rules of counting, of course. So we are again in the case where you can count objects. So we assume that the propensity is given by this constant kj, which is also the reaction rate, times now another factor which is called hj of n, which is now depending on the configuration. Now you have to, so in the modeling you have to think of this hj of n as something that is relatively small if some of the types are not present in the system which are needed for the jth rule. So this must be somehow something that is related to a combinatorial effect or low number effect of objects of certain types. We will see that in a second in the next slide. Now the other possibility we had with these weighted rules was that we have a function weighted rule that is given by fj of t and n. So again, the idea was that you have some influence from outside, so there is some time dependence possibly on the way the rule is executed, and there can also be some state space dependence on this function weighted rule. But again, this is just a factor in front of the same function hj of n, which keeps track of the collision mechanism. So this is a kind of probability that is related how certain objects of different types can come together and actually trigger the event. So this is an, you could also call that this is an intrinsic factor, and this here is some extrinsic system factor, which is modeled either by a constant kj or by a function fj. So how are these hj's defined in case of rules of counting, so you can count objects? Well, it is just given by this simple formula here. So it is first of all, you have to remember that the number of independent possibilities to choose k objects out of n objects. This is, how the objects now come together in a collision event, is given by this number cnk. And here every of the n objects is allowed to appear once in any combination. With this background, we now define the hjn as a product over all these factors nj over alpha ij, where nj is the entry in the state vector. So these you have the assumption here that you have n many objects of type I, and here that is the stoichiometric coefficient alpha ij on the source side. So this tells you how often with a given stoichiometry alpha, how often you can have type ni in the configuration. So how often could you trigger this event with different objects of type I? And each of these factors contributes for each type, and then the product of all of them is actually exactly the number hjn. So that means, if, for example, ni is of the same order as alpha ij, so there are just alpha ij many objects of type I in the system, then this factor here for type I will be very small, and then by taking the product, hjn cannot be very big. But on the other hand, if all the types are very abundant, then hjn is also a very, very large number. And then you can see by this combinatorial effect that then stochastic effects are not coming much into play. So this is exactly the structure of hjn, and we use the convention that n over 0 is just 0. So if there is no type I needed, then then this is just set to 0. So let's go right away to the classical Gillespie algorithm. Now this is a little bit small because it had to fit on one side, on one page, sorry. So let's make it a little bit bigger in the beginning. But now you should think of the following. We had the master equation. We had defined the propensities. So all the ingredients of the master equation are now explained, and they are in front of you. And now we create a stochastic algorithm which creates the stochastic process that is defined by collision events. So how does that work? Well, we have first to set the initial condition. So we start with an initial configuration n0. We start at time t0, say, and we fix a certain final execution time, capital T. And then the algorithm consists of these 7 steps. So now I make it a little bit bigger so that you can see it better. So the first step is to generate 2 random numbers r1, r2, uniformly distributed in the interval 0, 1. Then we create, in a sense, in step 2, a big propensity that is just the summation of all individual propensities coming from all rules. So this, in a sense, gives you the overall reactivity or probability that you can trigger the system. And we compute now a step with tau by the assumption that this is given by 1 over r0, the logarithm of 1 over r1. Yeah, then we set in step 4 the execution time to t plus tau, so that's a typical stepping step, time stepping step. And now the interesting thing is, and that is, if you remember, that is really the difference to the Poisson process. So in the Poisson process you would be ready now because you just want to know when the next event happens and then you count it. But here we do more. We compute when the next event happens. We have done that when we finish step 4. But now we execute exactly one rule and we have to determine which one we execute. And this we do with our second random number r2, which we have already computed before. And we do it such that, we look at the sum of all the propensity weighted by 1 over r0, such that up to the index j minus 1 of these rules, we are still less than r2. But on the other hand, r2 is less or equal than all the propensities where you sum up the propensity up to index j. So r2 is just in between, and then you execute rule rj, because the rule rj has just brought you over the threshold which was given by the computed random number r2. Yeah, and that will of course now update your system configuration. And then you go to step 1 and you are time stepping throughout. And this is exactly the Gillespie algorithm, the classical Gillespie algorithm. And you can nicely see that here the propensities come in. So, for example, if you have fixed R2 in step 1, and the propensities of the first rules are very high, then you will need only a few of them in order to get to R2. And and also remember that of course the labeling of the rules is completely arbitrary. So they are not ordered by any way. Okay, so this is the classical Gillespie algorithm. It works exactly in the same way for rules of amounts, but here you have to be a little bit more careful, because you have here the real valued state space. So you have to compute here stoichiometries of how often the stoichiometry goes into the substance, amount of substance that is present at time t, and then you take the floor function to get here an integer out of it, and then with that you can define the propensities exactly as before. And you also can compute the same kind of propensities, for example here with a function-weighted approach. And you have exactly the same Gillespie algorithm as before. Now this actually you have to be careful with Gillespie algorithm like here, because here you cannot have any time dependence on the propensities. So you can see that the propensities are assumed just to be depending on the configuration n. So what happens if you actually include a time dependence on the propensities? This case you have a slightly different Gillespie algorithm, which is both true for the rules of counting and for the rules of amount. So I will not go into detail of this, but you can see the major issue is here. So please look at this very carefully. So here you have only an implicit definition of the time step Tj, which you have to compute from an integral over propensities. And this then gives you the correct statistics for the stochastic process. Okay, so with this I would actually like to close today. So we have seen as a summary that you can model maybe actually in every area of science if you go through with this classification scheme and you set up the rules for certain discrete events which we are discussing here. You have seen that you can properly define a master equation once you have set up these rules, and the crucial step to make it a real stochastic process is to define these propensities. Remember, the propensities are just defined such that if you have a low number of particles in the system of some type, then certain rules or transitions are actually becoming extremely unlikely. This is exactly how it is in the real world. If you have, for example, a certain product, you need to produce other products, and this is not available, then the whole process in a certain sense stops. This is exactly how we modeled here the propensities. So that works. We also have included a time-dependent algorithm, so we can also from now on incorporate non-autonomous stochastic processes where, for example, we change some outside condition. Think, for example, of the epidemiological model. There will be, for example, certain closures that are imposed by the government. Something like that would create a time dependence on the infection process. So you have to have some algorithm that reflects that. If that is the best one or some other, we discussed at some later time, that I have to leave open at the moment. So yeah, please study all these algorithms and formulations carefully, and yeah, I see you very soon.